Okay, so we're going to do lab 2 today, another hands-on lab in Excel. And today we're going to learn about something called regression analysis, which is a very useful kind of data analysis technique where you take data and you use it to kind of create mathematical models that kind of describe the data, which is then helpful for other things like design and stuff. So when you're going off to your university and they give you labs and stuff, they're going to expect you to do some of these analysis operations on data to kind of understand what the data is saying. This is one of those things about, you know, have you heard of the importance of critical thinking nowadays? They want people to have more critical thinking skills. Have you heard of this in your education, critical thinking? This is one of those things, like they want to be able to like show you like data and then have you sort of make sense of what the data is telling you. That's kind of a critical thinking operation. So it kind of falls into that area. And engineers use spreadsheets a lot because it's more of an excuse to kind of work with Excel. So that's what we'll be doing today. I did have a lecture on the history of engineering, which it's not hugely important. It's not going to be on any quiz or anything, but it's kind of interesting. I don't know, we could maybe, are you guys interested in the history of engineering at all? How we got to where we are? It is sort of it makes you appreciate how far we've come when you kind of see how things go. In fact, there was an interesting website that was arguing that, you know, we think of ourselves in the year 2000, but that's really kind of misleading. It's not like time started at 2,000 years ago. We know there was stuff before that. And some people, I don't know, archaeologists or whatever, people that study history and all of humanity kind of suggest that we should maybe add another 1 to that number. So instead of being the year 2000, it's more like the year 12,000, which is like the year that, it was something like the year that there was like the first structure, it was like a religious structure that was built in Africa or someplace, or Mesopotamia, where they, you know, they were doing something, humans were working as a group, they were building something, and they kind of have this record of it. And yeah, I don't know. You can go back 40,000 years and you have the Asians migrating to the New World, and they have like evidence of, you know, chip stone tools and stuff that they were using still, you know, 40,000 years ago. So I don't know, but actually 12,000 years, that's kind of maybe the dawn of civilization, maybe 12,000 years ago. And that's a perspective that this kind of takes a look at, kind of that kind of time scale. And these came from my colleague, Dr. Hornstein at Hartnell College, who maybe some of you have taken or will take a class with her, because some of you are actually not too far from that place as well. They have a good program as well. So they are our rivals. Don't want to tell too much about them. But Melissa's very generous with some of her stuff and sharing. So anyway, so this is these are some slides that she put together, and she drew from one of the materials she drew from is a book called Guns, Germs, and Steel, which is has anyone read that book? It came out like about 10 years ago. Guns, Germs, and Steel. Guy was trying to answer the question, why was it that you know, Europeans colonized the world rather than, say, the Papua New Guineans? You know, why was it, you know, that things worked out that way? And he traced it back to, interestingly enough, he traced it back to the distribution of domesticatable grains around the world. There happened to be, of like the 16 grains that people could actually, you know, evolve into edible products, 11 of them occurred naturally in Mesopotamia, you know, places like Iraq and, you know, the Fertile Crescent, Israel, all that area there, which is kind of considered the cradle of civilization. There were 11, you know, like oats, barley, rye, all those foods and beans and lentils and stuff, they were all growing naturally there. And so they had a sort of a head start in terms of going to agriculture, and then led to more and more stuff. Anyway, it's a pretty fascinating story, and you can look in a broader perspective, not just agriculture, but just some of these, some of these inventions that have been around for so long that we don't even think about them as inventions anymore. And you can think about, where do they come from? Here we are, just kind of a list of some of the things. 10,000 years ago, this is about that, the dawn of civilization. Say 12,000 years ago, not much longer after that, people were using spear throwers, and you could think of this as a the start of maybe a kind of mechanical engineering. Mechanical engineering is about the harnessing of forces to achieve some goal. A spear thrower effectively lengthens the arm and therefore gives a greater force to the thrown spear. Why is that? How do spear throwers work? Yeah, well, if you think about it, there's maybe a limit to how fast your arm can actually move, right? And you put that in a circle. If you had a longer arm, the speed at the end of a longer arm is going to be, if the arm could kind of go with a certain, if you could say this takes like a second, right? If your arm was like 10 feet longer and you did that in a second, you'd be traveling a lot farther than if you're just holding it right here and going a second, right? So it increases the speed and the force of the spear on impact. So pretty clever design. Early agriculture, again, as I mentioned, one of the grains that was not in the Middle East was corn. This was actually an American local grain. This is in the New World, right? And corn, when it started, was about the size of a quarter. An ear of corn was that small, and it took the humans there years and years, hundreds, thousands of years to turn that into, through selection, an large edible product. That's an example of genetic agricultural engineering. You think about all these animals, some animals that could be domesticated, some that could not. They were not just distributed randomly either. A lot of those animals that turned out to be pretty helpful were also in the Middle East, goats and things, sheep. Anyway, some animals just turned out to be, you couldn't, like zebras. No one's actually domesticated a zebra because they're just so unpredictable. And that's the reason why a lot of animals could not be domesticated, just because of their behavior. Interestingly enough, there's an interesting story about trees. Almonds could be domesticated, but oak trees never succeeded to be domesticated. And the reason for that is because of squirrels. Squirrels kept us from turning oak acorns, which are very bitter, into something more pleasing or edible, because squirrels would grab up all the acorns and plant them as well. We couldn't really weed out the bad oaks and have our own oaks. The squirrels would actually just kind of run with them and just scatter them all over. So you couldn't really control the genetic content of oak trees very well. Anyway, this kind of shows you where ancient civilizations started forming, and you can see already, I don't know what year this was, but already the whole European area, this must be ancient Rome, is quite, I guess this is kind of over many time scales. Mesopotamia is this sort of turquoise blue, that's Mesopotamia region over there, dawn of civilization, kind of spread to Europe and things. Egypt was another great power, and so on. You can kind of trace where those things all sprouted up. Interestingly enough, the people had already migrated from Asia to the New World before civilization actually started. And these guys, they think maybe they had some kind of boats, or they just walked across a land bridge when the Ice Age was there. Because the sea level was so low, they could just walk across. Across this bridge between Asia and Alaska, and then on down. But anyway, it's a fascinating story, and anthropology is always something it's just so amazing. You think about how all this stuff happened. Here we are in Mesopotamia area, where so much So much strife is going on right now, unfortunately. But all these things, so, you know, development of a plow, mechanical kind of product. You got the yoke for oxen. Things kind of started up. Looms for clothing. Again, Mesopotamia. Metallurgy, materials engineering, working with metals, how they discovered that. What accident took place in some fire, you know, where they had some stones in there that kind of melted and turned into some metallic thing, and they're like, what the heck is that? And, you know, played around with that. Who knows, you know? Looking at just the wheel, none of these inventions were expected to be, you know, they didn't come out fully formed from some, you know, prehistoric person's head. They came out through evolution, just like, you know, natural products. Placing rollers beneath blocks is one way to move them. Runners would be a little bit more efficient. You could drag as a sled. Putting a runner on top of or a sled on top of a roller also makes sense. And then when you do that for a while, you realize, oh, that sled is cutting grooves into the log, so therefore, and noticing it actually kind of works better that way. You don't have to change the log as much because, again, for the same reason, when the radius gets smaller, the log will stay on that sled longer. And then, oh yeah, you can maybe keep that log in place with some pins or something, pegs, turning that into some kind of a bearing for an axle. Now you've got an actual wheel, you know. So these things are incremental. A lot of engineering products are just developed that way. Just you have the great idea, but then it takes a lot of refinement. Interestingly enough, 2000 BC, about 4,000 years ago almost, they had some ethics about, you know, if someone builds a house and it falls on them, the builder shall be put to death. Oh, causing the death of the owner. So if the house kills the owner, then the builder also has to be killed. Wow. Eye for an eye here, right? The death of a son of the owner shall cause the son of that builder to be put to death. So that's how it was if you were a civil engineer. They didn't have insurance and malpractice insurance in those days. Towers and things, people built all kinds of interesting structures back then. Egypt, you've got irrigation systems, another huge invention, right? Getting water to people. You've got all kinds of work. That's a civil engineering area. You've got construction, pyramids, another big civil engineering area. Rollers. Why did they use carts to haul those blocks across the sand? Sand, yeah, they would just kind of fall into the sand, right? Rollers would be a better way to do that. You had Greece with their ships. You had better metals. So bronze is actually pretty good metal, but it melts at a, you know, I don't know what the temperature is, 1,000 degrees. Iron is actually much higher, so you need to have a higher furnace, but, you know, bronze becomes a stepping stone to better metals like iron and other ores and things, so other alloys, kinds of things. You've got this, I think, never actually, you know, this towering giant of a figure, I don't think this actually really was present. This is the, does anyone know what this is called? This is the Colossus of Rhodes. Is that what it is? Yeah. I was trying to look it up, but I think that's sort of, I don't know if that really was a real thing or not or whatever. It probably wasn't as big as that. It just seems like. If people could do that, you know, they'd have computers by then. All kinds of stuff, lighthouses, aqueducts, all these things, you know, satisfied needs. You've got weapons, mechanical engineering again. There's a saying about the difference between mechanical engineers and civil engineers. You ever heard this one? Mechanical engineers build weapons, civil engineers build targets. Kind of cynical. Archimedes and the screw pump. This is actually pretty cool. And you can kind of visualize this thing working. You know, what if you were, you know, in some reality TV show and you had to figure out how to pump water? This is actually, you had a hose. You could actually do it. Just wrap the hose around a stick. You keep cranking that thing, and it automatically just shoves the water to higher and higher levels, and it comes out at a higher level. Pretty amazing. Archimedes pump. Yeah, all kinds of things, water wheels, roads, structures again, civil engineering, arches, the importance of arches and distributing forces, bearings. This is just 100 BC. So yeah, most of the fields are predominantly civil with some mechanical. Civil was just really important and in the growth of civilization. It looks like there was a military engineering and a civil engineering up until the 1880s, and they called it mechanical engineering. Electrical engineering starting in the 1800s. You can kind of see the growth of different fields. Civil was the kind of the earliest one, marine, materials, mechanical, all these things. Electrical, 1850. SW must be software. Yeah. Anyway, what do you make of all this? What does that tell you about humans? Yeah. Yeah, it's like part of our DNA practically, right? Anything else? Pretty important to our society, to maybe who we are, that we, you know, of all the animals on the planet, we are the only ones that kind of really started messing with stuff in a way that made it better for ourselves. So, yeah, I mean, I think it's like you can argue that, you know, we're called Homo sapiens, you know, that's sort of, sapiens is an indication of like wisdom, I guess, right? We're supposed to be wise humans, but maybe we're more engineers than wise, you know. We actually make stuff pretty readily, right? That's a lot of what we do. Maybe we should be called Homo whatever. Ingenuity. Homo ingenuity. Anyway, that's the lecture for today. The rest of the class we can spend working on the lab. So the lab is a bit of a data analysis thing again. And I was trying to kind of, in the material I got from my colleague, they were doing stuff with springs and, you know, putting masses on springs, the kind of thing you would do in a physics experiment. Not terribly exciting. I thought this would be a little more interesting, and we can do a couple of these things. My thought was, suppose you need to design a new office chair, and you want to make it suitable for tall people. I have this problem with furniture. A lot of the furniture I sit in is obviously designed for short people, and I end up like, you know, having to slouch, or, you know, my knees are sticking up to my chest. It's really annoying, right? So what if you wanted to figure out, you know, well, okay, suppose you want to design a chair so the armrest is sort of like about the proper length of the person's forearm, who's perhaps 6 feet tall. You want to make a special chair company for tall people, right? And so you need to do some analysis to figure out, well, how long should that armrest be? What are you going to do? Well, one thing you might do is you might measure a bunch of people. But another question might be, suppose you're an archaeologist, and maybe you found an arm bone, and you want to figure out, well, how tall was the person that arm was attached to when they were alive, right? So you might want to go the other way. You might want to go from somebody's height to the length of an armrest, or from somebody's forearm to like how tall they actually were. This is something that scientists like to do all the time. Is people take information and kind of figure out something else from it. So this is kind of a science experiment that we're going to be doing, but it's useful a lot in engineering. We want to maybe get some understanding of the height of a human versus their forearm length. And we want to be able to take that information and make something useful out of it, like a mathematical formula. Because if we knew a mathematical formula, then you could just tell, you know, if someone told you their height, you could sort of figure out how long the armrest needed to be. Or if you knew someone's forearm length, you could figure out pretty much how tall they were. But then how accurate is that? You know, we want to kind of think about these things. And a regression analysis is how you actually work with data in that way. We're going to kind of play around with that in the lab today. There are these regression equations that kind of explain how this all works. And this might be a little too, it gets a little mathematical. But we're going to be applying this, and so you'll kind of get a chance to kind of get a hands-on feel of it. So and part of this involves equations of lines, which is how you represent a straight line in mathematics. some statistics and all. We're going to be creating scatter plots, and we're going to be using Excel's regression equation, regression features as well. So you all know this, right? Well, I mean, is anybody not? Where do they give you the equation of a line? Is that algebra or algebra 2? Is it algebra? Okay. Is anybody? Because some people actually are not yet in algebra. Has anybody not taken algebra yet? Okay, good. So you all know this equation: y equals mx plus b. And you can, I guess, write this differently. Different formulas conveying the same information. This is the, in the terms of data, what we're going to have is sort of, when we take a bunch of data, we're going to have a bunch of data points on a plot, which are not going to be arranged in a line. There's going to be some noise and statistical variation in them. And we're going to try to fit that data with a straight line, the best straight line that we can, to come up with a mathematical equation for describing how that data actually is organized, how it's related. So as an example, here's some data, right? And the idea is what we're trying to do, this might be the data that we collect. You know, we want to maybe we want to fit this data with a straight line. So it looks something like that. And we come up with a mathematical formula for that, y equals mx plus b. We have to figure out what m is and what b is for this to work. And this would be considered a positive slope. If we have a positive slope, what does that tell you about m? M is greater than 0, right? And a negative slope is where m is less than 0, right? And it would be fit with a line like that, right? So that's all pretty basic. And then a lot of times what we want to do is we want to explore how data is related. So on this plot, we might be plotting something like your forearm length versus your height. And if you see something like this, where the data is sort of arranged in almost a linear fashion, you could say that there's a strong linear correlation. Now, we don't know if there's a reason why a forearm length would be associated with your height. It kind of makes sense, though, that it would, right? That, you know, tall people are going to have longer bones in general. So you'd expect that to be fairly correlated. On the other hand, some things may not be that correlated at all. If you have your data kind of arranged in a cloud-like pattern, it would be kind of hard to fit a line to that and make it kind of have any sort of meaning. On the other hand, there's some that are in between where there's a cloud that's sort of shaped in a linear way. So you could fit a curve in there, but you'd want to have some indication that this was not necessarily a terribly close and precise fit. And that's what regression analysis does for you. So what you can do is you can take a bunch of data in Excel. We've already seen how to plot that, where you have some price, maybe a number of bids. This is actually a study on like eBay. I think they were looking at some product that was being sold, and they're trying to get a figure of, you know, how does the price of the object relate to the number of bids that it gets. And oddly, it seems like the more expensive the item was, the more bids it got. That might be useful, right? If you're trying to figure out how to price something you're selling. I've actually heard this, like, you know, like sometimes like whiskey companies, they'll actually sell, they want to like sell a product, you know, for really cheap because they think more people are going to buy it. But it turns out they'd actually make a ton more money if they like double the price, because then it seems like it's a more expensive whiskey, so it's obviously better. So people are willing to pay more for it, right? Just weird psychology stuff. And you can collect data on this and sort of figure out, well, what would be the optimal pricing for a product you can sell. So in Excel, there's a feature to add a trend line, and on the trend line on this thing, you can have it display the equation, so you can actually figure out, after it does the fit, you can figure out what is that equation. You can use that in the mathematics of what you're trying to do to get to the understanding better. So it'll look something like this. When you finish your analysis, you'll get this equation of a line on there. And what this is telling us is an equation that correlates. What's y in this case? Is y the number of bids? Okay. And then x is the price in dollars, right? So the idea is, if you decide you want to sell this thing at $50, it's not even on this chart, you can kind of get a sense of how many bids you're going to get for it, right? You just plug in the X of 50 and do the calculation. That should sort of tell you how many bids you would expect to get for this product, basically, right? And it's fairly correlated. Looks like a pretty good correlation. We will do this together. I always have to kind of figure this out. There's another fun example. Does the unsupervised student, this is a, I think this is for like high school. Does the number of hours a high school student spends unsupervised impact their overall grade average? What do you think? Is it going to be positively correlated or negatively correlated? Negative correlated means it's going to have a negative slope. So you would expect the more you leave a high school student unsupervised, the lower their grade is going to be, probably, right? You can't trust them on their own. And sure enough, you can see if you leave someone for 5 hours, their grade average is quite a bit lower than somebody who isn't unsupervised at all. So you make a plot of that, and you can kind of see the way it looks, and then you can fit a line to it, and so on, and you get that. So that's what we're going to basically be doing in the lab today. So we're going to pull up the computers. We're going to do some examples and take some measurements. Just like before, you're going to work in teams. So each team's going to get a year stick. You're going to make a lab report when you're done. Did you get any replies to your email? What about the email you sent? So, yes, you can't.
You got this, or you rent?
Yeah. And this is the lab handout. Lab 2. Okay, he's working up. Okay, so here we are, and we're doing lab 2. And again, we're going to use Excel. I think you might be able to do this in Google Sheets, but I haven't done it in Google Sheets, so we're going to just use Excel. And this is the lab. First, actually, let's go to the let's go first to the Google Sheet for data collection. So in the lab on Canvas, there's this link called Google Sheet for data collection, and if you click on that, hopefully this will work. This is going to be the place where you're going to dump the data in a second. But for now, this is a place where we can receive the data. And what I'd like you to do is just copy this information by clicking and dragging across that table. And then you can say edit copy. Are people still logging in? I might be going too fast. Don't get logged in yet. There, you want to copy this and then open up Excel and just paste it in there. That's kind of how we'll do it. That's how we'll do it. You're going to go to the Lab 2 link on Canvas, and then inside that there's a link to the Google Sheet called Google Sheet for data. Find that? There you go. Yeah, just copy it to a blank one. And pardon me? Can you say that again? It's under Lab 2. Did you find it? Good. I can. Is anyone having problems locating the Google Sheet? Okay. All right. So then you can open up Excel. And paste it into a blank Excel sheet. Oops, there it goes. And that didn't work very well for me. Did you guys have that same problem? Let's see. What did I do wrong here? Try that again. Here we are. Now let me pull this thing, get down. You know, maybe the better thing to do actually is to just download this thing as a sheet. I don't know, it didn't seem to copy into my Excel very well. I'm going to close that. And because in Google Sheets, you can also just download the whole thing as a Microsoft Excel document. That's probably a better way to do it. And then after it downloads, you can just open it up and it will open in Excel. Why is this not cooperating? Let's try that again. And if you do that, it's going to complain that this is from the internet, so you have to enable editing. And you should then have the data, however you did it, if you copied it and pasted it, or you downloaded it, you should have that first example there. And here we're going to do the plot. So basically, to do the plot, you're going to highlight all of the data, both columns, and you are going to insert another scatter chart, which is under here. Just do the scatter chart like that, and move that into a respectable place, something like that. So this is our chart. That we can then fix up. You got that? So highlight all, insert to the scatter chart. Okay, so also another thing to point out, whenever you're doing a chart, what I want you to do with a chart is you got to have labels for these axes, right? I don't want to see, like in your reports, if you just say number of bids, that doesn't really help me understand what this chart means, right? If you just saw this chart, would you understand what the heck it meant? No, right? So what you would do is you want to click on these chart elements, and you want to do an axis titles at least, so you kind of know what these things mean, right? So you're going to click that, and now you can type in axis titles. And this was the, what was this supposed to represent? Price in dollars. And this is the number of bids. And you might change the title, because the title, it just took the title of the dependent variable. So we could just say number of bids versus price in dollars. Okay. And you know, for eBay sale or something like that. Anyway, so that's your data. Now, the other thing we're going to do is we're going to add that trend line. So it's actually pretty straightforward. And we're going to go back and click on, let me see, just click outside of that. So get out of there and go a little bit to the right and go back to that plus sign and then go and click on trend line. Trend line, and you're going to choose linear. And let's go down more options and see if we can get that to show up. We want the trend line, we want the equation to be up there. So where is the trend line options? It's all the way at the bottom. I don't see it. Which one are you doing? Oh, the chart thing? There we go. That chart, the bar chart thing. And you're going to say, where does it say that? Display, equation on chart. Yeah, also, by the way, the R squared value is also very valuable to indicate how good of a correlation it actually is. Okay, and then you can click back on there, and so you should have that. My onboard screen is just going crazy. I have to figure out what's going on with this thing. But if you did it, the way I did it, you should have the equation as 0.2299x plus 1.7356. And the R squared value is 0.9195. Okay. Anyone have any problems with that? My TA will be happy to help. Click on the display R squared value. Anyone else have any problems?
Just minimize it.
It's sort of like so we can fix it. R squared is a formula calculation. It basically, so this R squared term, I don't know if that's described on our handout. Let's see. There's actually a lot more to it on the handout, which it might be interesting to try to put that together. And since the lab itself is not terribly complicated, we could try that. But let me see here. Let's go back to the lab, which is right there. Of course, Excel makes it look really easy. But this is actually, linear regression is based on a technique called the method of least squares, which is something that comes from linear algebra, if anybody's in the linear algebra class. You start by collecting a set of sample data points, a bunch of x values and a bunch of y values. And the method of least squares is it's sort of illustrated by this. You basically take so we're trying to take so we're trying to predict essentially the y value of a particular x using this formula m times xi plus b. So this is like a prediction. We're going to use yi to denote the ith observation and y hat of x to denote the predicted value. In other words, this is a functional representation, and I think functions are a little bit more like in Algebra 2. But what they're saying is you can predict y given an x using the formula mxi plus b. And you can compare that with the observations, right? So this is the cool thing about it. This is one of the cool, I used to use this so often. It was just so awesome. So in other words, the dots on the chart here are the yi's. And the point where the line kind of goes above or below the dot is like the prediction based on our formula. Now you notice there's an error between each of those, right? The dot doesn't fall exactly on the line. And if you take all those errors and you square them, that's kind of helpful because if you just add them together, you might have the positive dots canceling out, the positive errors canceling out the negative errors, and you might look like you have a really good fit when in fact there's some big errors there. So what we do is we square the errors, meaning they're always going to be positive, and you add those values together. And that curve, that formula, is the formula that provides the smallest sum of the squares of all those little errors. So it is the best fit when you square the errors and add them together. You can get the smallest amount. And you can do some experiments by trying, equations that are a little bit different. You can see that some of the squares actually get bigger. And it actually is probably possible, although I would have to kind of noodle through this a lot. I'm not really set up for that. To try to actually do this formula in Excel, if you were crazy enough, you do this by taking partial derivatives of the expression with respect to a and b. I think they mean m and b, m being the slope and b being the y-offset, and setting the resultant to 0 and simplify, you can get this formula right here. Yeah, here it is. So that is a formula for computing the slope and the intercept. And the standard error, the RMS error, is defined as 1/square root of the yi's minus the y observations. So actually, this is actually something we could do. The first two ones are going to be kind of hard to do, but we could actually compute what the RMS error is. The root mean square error means we take the errors and we square them, and we add them all together and divide by how many there are. So that's the average of the errors squared. That is sigma. That's what's sort of being minimized. And that can give you a range of values for which the actual slope lies in. So that gives you what's called the confidence interval. A common interval is 95%. The 95% confidence interval is specified by m minus 2 sigma through m plus 2 sigma. What does that mean? That means the slope. And should we do that? Let's see. Sigma. That's going to give you, yeah, plus or minus 2 sigma. So let's do that calculation. That's actually kind of cool. Let's do the sigma calculation right now. That's actually not too hard to do. We can add that to our table. So if you go back to the actual table, so this is your price in dollars and number of bids. We can actually then put our formula estimate in a new column, and it changed the format. So I'm going to click, if you want a format to change, you can click on that and click on the paintbrush. You can copy the format of one cell to another cell like that. And the equation says our formula is 2.99x, 0.2299x minus 1.7356. So you can say our estimate is going to equal 0.2299 times, and what is x in this particular model? Talked about this already. It's what? Price in dollars. So we're going to click on that 28, which is mine is in B6, and then we're going to add 1.7356 to that, or minus. It's minus, right? Minus 1.7356. And what? Yeah, oh yeah, that tells us it expected 4.7 bits. Now again, the format stinks, so let's copy and click a cell that you like to format on, use a paintbrush, and then click on that, and you'll see it much nicer. And then you can drag that down, and you can see those are the model estimates for all of the number of bids we have, all of the data points we have in our curve, right? And you could also ask, okay, well, what if I did set my price to $50? That's not in the model. What would my expected thing be? Well, I had it pulled down. It said it would be 9.7. You expect 9.7 bits. I don't have any data there, but I can see that I can use this formula to make predictions, which is pretty handy. We like to predict things. And then sigma. Well, to find sigma, this says formula estimate. I know my formatting is kind of really crappy here. You might stretch these things out so that they don't actually run over each other. You can compute the error. Oops. And also the square of the error. And so the error is just going to equal this square minus that square. And we pull that all the way down. And then we want to square all those numbers. We can forget this new estimate of 50. Forget that guy. We won't worry about that. We'll have an error there. And then we're going to square all these guys. And so that's going to equal this guy, shift 6, 2 is going to square it. It's very simple. For the error, I'm just subtracting the actual data minus what our formula estimate was. That is the error, right? The actual data was 5. Our formula said, we predict you're going to have 4.7 bids. We actually got 5. The formula says, we predict 6.3 bids. You got 6. So the error is just the difference between those two columns. And that's the same thing as what we're seeing here, right? That's these the little differences between the dot and the line. That's what we're actually showing. Notice in the first one, it's actually positive, and the second one is actually negative. And depending on how you define these, I think we might have, our sign might be flipped and we find the error, but no, actually it's the same. Yeah. Yeah, the square of the error is you're just going to take the error column. So you click on in this new column, you're going to go back and click on this column, on this guy, and then put a shift 6, 2 on there. That's going to square it. And you pull it all the way down, and you've got, whoops, you've got the square of all the errors. Question? How did I what? Yeah, for the formula estimate, I took this formula that our regression line came up here, which is on the right here. It's y equals 0.2299x minus 1.7356. And instead of x, I clicked on the cell of what that was, right? So the formula estimate is 0.2299 times, and then it's the B, which is the column to the left, price in dollars, right? Minus 1.7356. That's what our formula is. Okay, why don't you just watch? It's okay because this is just a demo, and then finally we can figure out. Remember what that confidence interval says. The confidence interval is sort of how reliable is our, what are the uncertainties in our estimates. So sigma, we can make another row here for sigma, and what we're going to do for sigma is we're going to take and add, looking at the chart. So we just computed these are the errors, and we squared them. We're going to add them all together, divide by how many there are. That's basically the average. And then we're going to take the square root of that. And that's going to give us like the plus or minus error bars on our model. Does that make sense? So we're going to, it may not make sense, but it seems like you should be able to do that, right? And so actually what that is we're going to take the square root of the average of all these cells. And it says 0.4. I selected them. So I'll show you how to do that again. You type equals SQRT, open parentheses, average, open parentheses, and then you just click on the first of the range and you drag to the bottom of the range. And you do close parentheses twice, and you get a number, sigma. And then that sigma means that whenever you come up with a formula estimate, you're supposed to say, well, that's accurate to plus or minus 0.4 with a 95% confidence. That means 95% of the time, the true answer is going to be within 0.4. Sigma, which is going to be, I'll show you the sigma formula again. So this is the formula that I typed in here. For the average. And there's just one number. You don't pull this down. There's just one sigma. It's an aggregate of all of the errors.
Click on number of bids. Pick that up.
This one?
Pick number of bids. Pick that up.
Number of bids?
Pick that up. And then click. No, don't select it. Select it. And then the corner you should pick one.
What's it over here?
Yeah. Does that let you select that format here? No, you don't need to select all of it. Just yeah, see? Now hit the big one.
Click on that cell.
Now hit the cell you want to change. Now look, click the cell you want to change. The same paintbrush again. And you go to the next one. Go back and click on the one that you get.
Thank you.
No, No, you ain't, don't select everything. Just select the cell. Click on a different cell and check back to it. Now hit the
Thank you. The final question.
Okay, so I asked you, if I ask you if your model comes up with 7.4, what are the plus or minus that you put on that number? So in other words, someone says, I'm going to set the price at $40. Well, my formula is going to predict 7.4 bids, plus or minus what? 24. Although, is it 2 sigma or just sigma? Wait a second. What does the handout say? It's 2 sigma. So that would be plus or minus 0.8 to get to a 95% confidence interval. What does 95% confidence interval mean? If you do this, if you do like 95, if you do 100 estimates, like you have 100 different prices you're trying to do the estimate for, and you add plus or minus 2 times sigma, so plus or minus 0.8, 95, and then you, in truth, you figure out how many bids you got. 95 of them are going to be within plus or minus 0.8 of your guess, of your estimate, not a guess, of the estimate from your formula. The true value will be 95 of those will be within 0.8 of your estimate. That makes sense? 5 of them will be outside. Statistically, you're going to have some of them sort of fall out. A little statistic, so that's very helpful in understanding. So again, if you're making a chair for tall people and you have this formula, you know, you do it this way, you can figure out what your confidence interval is, and maybe you can make some adjustments to your design to take into account the fact that some people are going to not fit in so well. Well, that took a lot more time than I thought. There is another example, which, but it was fun, I hope, which is the teen unsupervised. We can skip that one. And let's do the next one, which is forearm length versus height. Now, in this one, we're going to be experimenting with live human subjects. In other words, you guys. And because this is an experiment done on students, I cannot ask for your name. So you have to provide a code name. And what you're going to do is you're going to take your measurements. Everyone's going to take your measurement and type in your number in the Google Sheet. And then when everyone has a value in there, we're going to use that data and analyze that and provide a model between forearm length and height. Okay, so the thing is, I have to go to the Google Sheet, which we went to already. This is the sheet right here. And on this one, we have and you know, you can measure your height, but maybe you know your height from memory. We do have meter sticks if you want to try to measure that, but it might take too long. So if you know what your height is, everyone, you kind of all know what your height is, right? If you don't know, then you can grab it and try to measure it. If you do sort of know it, just use that. And then you're going to measure your forearm length in inches. So we'll do all this in inches. And then you're going to add your name here. Now it's going to be kind of fun when I allow you to do this. So basically, I have to do the sharing settings, and I'm going to allow anyone with the link can edit. So you're all free to just completely change this thing. Just please don't change anyone else's data. Please respect the sanctity of scientific experiments. And if you see a cell being occupied, then don't type in that cell. So in fact, maybe right initially you might want to just claim your space by putting a code name somewhere. So just type in a code name for yourself. And that way nobody else will use that row. And you can always go lower. At the end, I'll just sort it all. And then you can, you know, all the spaces will be removed. So are people typing in their code names? Yeah. Yeah, so type in a code name. And then that'll be your information. And And then what I'd like you to do is enter your height and your forearm length, and we'll do a statistical analysis of that, and we'll get a sense of what is the mathematical relationship between height and forearm. Go to lab 2 on campus. Yeah, the pattern sheet is on forearm length versus height. It's the same sheet we looked at already.
Where's that one?
It's up to.
Otherwise, we're going to take tomorrow and not going to be able to get this.
Well, you can enter your data. Yeah, well, the way you're going to do the measurement, thank you for asking. We got to measure it to a known spot on our hand. I think the best thing to do maybe would be to, I think the most standard way of doing the measurement would be to maybe put your hand on the table and measure the height from the table to like a little point on the edge of your elbow. With your palm flat on the table, please. That works? Does that work? Is that too awkward? Maybe that's not a good idea. How about we just do it? I think it'd be easier to just do it this way. Put your elbow on the table. Okay, put your elbow on the table and measure it to the crease. Everyone probably has a crease right there, right? So measure it from the table to the crease. I got like 12 inches. No. You're gonna measure to that crease. If it isn't exact, you should add like a decimal point too. If it's 0.5 or 0.7, try to estimate fractional amounts. Don't put like an inch symbol in there. Just put the number. We don't want to have units in there. Yeah, don't put like the inch symbol, like the quotation mark. Don't do that. Just put the number. And here too. Yeah, just put the numbers. And again, don't put 6'1", put actual inches. You gotta do inches in both of these. Don't put FT, put inches. 72. You're allowed to put that whatever that is. Okay, try to get all your data up there in another minute or two.
Everyone's like getting the phone, but no.
Yeah.
Okay, really cute.
Isaiah Thomas.
Okay, is that everybody? Anyone still, Kim K, are you almost done? Pat Mahaney, what's taking so long?
Oh.
I'll redo it. Wombat, what's your height? Okay, Kim K, you have 2 seconds to finish. All right, I'm going to wrap it up. Guys are going to screw up my experiment. Okay. You had your chance. So I don't think. Yeah, okay, that seems reasonable. All right. So we're going to. Clean up the data a little bit. Hopefully you're not able to change it anymore, but anyway, and this guy, I told you I want it in inches. Oops. Okay. And what is up with the filtering on or something? No, filter. Okay. And delete this guy. And Chuck Norris is gone. Sorry. We had a really nice format, but didn't provide all the data we want. Everybody else is okay. All right. So now you can grab this data. You could download the whole thing again. And another Excel document. And then open that. And then what you're going to do is, following the instructions, you are going to make your own model. We're not going to do experiment 2, so you can skip that. Well, anyway, using Excel, create a scatter plot. Oh, you know what? I got to sort this by increasing height, I think. Otherwise, the scatter plot will be all messed up. So I'm sorry. I'm going to have you redo the download a second. And so I've got to sort this beforehand. I think otherwise it will get really screwy. Without sorting it, really? Okay. Okay, good. Then don't worry about that. So you're going to compute, do everything we just did. You're going to compute that sigma calculation again, like we just did. So the sum of the squares of the errors, the average of those, and the root. That's going to be our sigma, and that'll be allow you to answer the question, how much uncertainty is there in your estimate? And you're going to do another report, just like we did this week. So you can grab that general report outline and start in on that. Again, this is a team effort, so you guys can work on it. One person could start writing the report, another person could start working on the analysis, and when you're done, everyone's going to turn one into Canvas.
So yeah,
No, you can do it without sorting. So yeah, just use the data as it is. Someone figured out that it works okay even if you don't sort it.
So the report is just going to be on the second draft reading, or is it on the photo?
No, just do the report on the analysis of the forum.
Oh yeah, I saw that.
This should be an axis. This should be an axis. This should be an axis.
Okay, there's a data anomaly you're going to have to fix. Somebody left a 5.9 in their data. Maybe not. Maybe just you got one. They would have 5.9 in the data. Yeah, okay. So you guys are good. So let's work with it. Yeah, so that's
That'd be cool. Like,
and also change the yeah, it'd be nice to not have yeah. So X is an horizontal axis. And you do the height. Oh, that air should go a lot smaller. So drag that one over there. That's where the air. Then you gotta add the sigma there. Yeah, that goes all around. Put all that in your thing. No, just that one guy. Sure, yeah. So they do.
What if it doesn't all fit?
You could do a screen capture. Yeah. Yeah. It's the same exact.
Square root, and then all the square root average. It's
Well, two signals.
so double plus one. All right. Square root. It helps you out pretty much.
So signal is that can define the model has and so what we're saying is
I had it earlier.
and the R squared value is like one.
Okay, so it's the same one. Okay, so you see okay, so to get this, use this equation remember. Yeah, so you're using the same thing. Make sure you get and then when you get it, yeah, fix it, get the equation and everything right. All that. Yeah, they pretty much say get the estimate right, and then get the equation for it, and then
I'll make the horn do next Sunday. Yeah, if you're still waiting.
What do you do after Italy? And then you're gonna click this and minus, right? This, that one's there. same
So
thing.
you should know answer correctly.
So, so like basically, you know,
And then that equals, and then put that, and then square, square. And then that's it.
And your signal is like. And I think the sigma is so large because you guys were just playing around with those numbers. That's what we decided seriously. We got terrible data set.
How do I do the sigma? How do I do the sigma?
Average. And the first is square root, then average.
Oh, yeah. You're doing something like that. It's your.
And then average. And highlight the yeah. And then close it. And then close it.
Did you get the formula?
Highlight down. You got different numbers.
There. You're seeing numbers as you.
You don't have no decimals.
I have decimals. I have decimals.
I didn't go past that. I each showed about away.
No.
Did you get the errors? Equal sign?
Yeah.
And then highlight the other one?
Oh, look. Look here. Okay, look here. Yeah.
The words they use.
I can just have a title.
Oh, type.
Yeah, you put it into the appendix of how long you're down.
Clearly, people need more work with analyzing.
Estimation, right?
Pick something out.
And that conversions different numbers.
Yes.
This
So not spiritual hours. Yeah.
This is the height. Yeah, that's height. Which measure the height.
And now it's you just
Oh, that's for me.
oh, yeah.
So you're already in row 12.
This color. And this is so that's like a proxy.
No, I think it's it tells you on canvas. Can I grab that?
This is subtracting the igual para sacar el square es lo mismo every square word va a ser square bien para sigma
El nombre es Sigma, pero mucho mejor.
el sigma va a ser la paréntesis square lo tienes que intentar así.